Every time you send a text message, watch a video, or train a neural network, you are dealing with compression. But how small can data actually get? Is there a fundamental limit? In the 1940s, Shannon answered this question, and his mathematics turned out to be the backbone of modern machine learning. Today, we will rebuild that theory from scratch, starting with a simple robot on a distant satellite. By the end, you will see why predicting the next word in a sentence is mathematically identical to compressing that sentence. And you will understand why some researchers boldly claim that compression is intelligence. The key insight is that information theory provides a quantitative measure of uncertainty, and that measure directly relates to the minimal number of bits needed to represent data without loss. This connection between probability and code length is what makes compression a fundamental concept in AI, as it underpins the loss functions used in training large language models. Imagine a robot on a distant satellite. We send it movement commands, up, down, left, right. But these commands are not equally likely. Half the time we send up, a quarter down, and an eighth each for left and right. Each command is independent, like flipping a weighted coin. Our goal is to encode these commands into the fewest bits possible, because every bit costs money and bandwidth. A naive approach uses 2 bits per command, 00 for up, 01 for down, 10 for left, 11 for right. That works, but it ignores the uneven probabilities. A smarter student notices that common commands should get shorter codes. This is the essence of variable length coding: assign shorter codes to more frequent symbols, reducing the average number of bits per symbol. The challenge is to ensure that the codes are uniquely decodable, which requires a property called prefix freeness, where no code is a prefix of another. The smart student proposes a variable length code: up gets a single bit, 0, down gets 10, left gets 110, right gets 111. Now, the average number of bits per command is a weighted sum: half the time we use 1 bit, a quarter use 2 bits, and an eighth each use 3 bits. That gives 1.75 bits per command, better than the naive 2 bits. But this raises a critical question: how does the robot know where one code ends and another begins? The answer lies in a property called prefix freeness. No code word is a prefix of another. That way, the robot can read bits one by one until it matches a complete code word, with no ambiguity. This is analogous to how Morse code uses gaps to separate letters, but here the code itself ensures unambiguous parsing. The design of such codes is a fundamental problem in information theory, and the optimal solution is given by Huffman coding, which produces codes that achieve the entropy limit for a given distribution. Now, the theoretical student argues that a perfect compression algorithm must produce output that looks like random noise. If every possible message of n bits is equally likely, then each has probability 2 to the power of negative n. Taking the negative logarithm base 2 of this probability gives n, the number of bits. This leads to the definition of information content. The information of an event with probability p is log 2 p. This is not an arbitrary definition. It falls out of the requirement for optimal compression. The more unlikely an event, the more information it carries. A certain event carries 0 information. This definition is intuitive. If something is surprising, it conveys more information. For example, a coin toss that lands heads has information log 2, 0.5, equals 1 bit, while a guaranteed event has 0 bits. This measure forms the basis for quantifying uncertainty and is central to data compression. Entropy, denoted H, is the average information per symbol. For a probability distribution over symbols, it is the sum over all symbols of p times log 2, p. This measures the average number of bits needed to encode a symbol from that distribution. The more uniform the distribution, the higher the entropy, because there is more uncertainty. If one symbol dominates, entropy is low. Shannon named this quantity entropy after a suggestion from John von Neumann, who joked that no one really knows what entropy is, so you can win any argument. The Noiseless coding theorem states that no code can beat this limit, but you can approach it arbitrarily closely. This theorem provides a benchmark for any compression scheme. The average code length cannot be less than the entropy, and there exist codes that achieve lengths arbitrarily close to it, such as arithmetic coding. In real language, probabilities are not independent. Each new letter depends on the previous context. The probability of a whole sequence is the product of the probabilities of each letter given its context. When you take the negative logarithm, the product becomes a sum. This is the beautiful part: the information of a sequence is the sum of the information of each symbol, given the context. This additive property is what makes entropy so useful. Even if individual symbols have fractional information, the total can be calculated exactly. This is the basis for cross-entropy, the loss function used in training large language models. For example, in a sentence, the probability of the next word given the previous words is used to compute the total information of the sentence. This chain rule allows us to decompose the complexity of a sequence into manageable parts. Let's compare the two approaches directly. The naive code uses a fixed 2 bits per command, ignoring probabilities. The smart code uses variable lengths, giving shorter codes to more frequent commands. The average cost drops from 2.0 to 1.75 bits per command. This is a 12.5% improvement, but the real insight is that this is not just a trick, it is the beginning of a theory. The smart code is actually optimal for this distribution, because each command's probability is a power of 1/2, so the code length exactly matches the information content. In more complex settings, we need a more general approach, such as Huffman coding or arithmetic coding, which can achieve the entropy limit for any distribution. The efficiency gain here illustrates the principle that leveraging statistical regularities can significantly reduce the cost of transmission. In modern machine learning, training a language model involves minimizing cross-entropy loss. Cross-entropy measures the average number of bits needed to encode a sequence using a model's predicted probabilities, when the true probabilities are different. It is defined as the sum over symbols of the true probability times the negative log of the model's predicted probability. Minimizing cross-entropy is equivalent to maximizing the likelihood of the data. And here is the key: the minimum possible cross-entropy is the true entropy of the language. That is why training a model to predict the next token is the same as compressing the text. The model learns the statistical regularities of the language, effectively building a compression algorithm. The better the model predicts, the lower the cross-entropy, and the more compact the representation of the text. This chart shows the average number of bits per command for the two coding schemes. The naive code uses a constant 2 bits, while the smart code uses 1.75 bits on average. The difference is small but significant. In a long sequence of commands, this saving adds up. The smart code is not just a clever trick, it is a step toward the fundamental limit. The theoretical limit, given by the entropy of the distribution, is exactly 1.75 bits. This is the minimum possible average length for any uniquely decodable code for this distribution. The chart visually demonstrates that the smart code achieves the entropy limit, while the naive code is inefficient. This illustrates the principle that optimal coding requires matching code lengths to the probabilities of the symbols. Shannon wanted to measure the entropy of English. He conducted experiments where human subjects guessed the next letter in a text. By recording how many guesses were needed, he could estimate the probability of each letter given the context. This is a clever way to probe the language model inside a human brain. He found that with at least 100 letters of context, the entropy of English is about 1 bit per character. That means English can be compressed to 1 yes or no question per letter. This is a remarkable result, and it shows how predictable language is. Modern language models can approach this limit in practice. The experiment highlights the connection between prediction and compression. The better a model predicts the next character, the lower the entropy, and the more compressible the text. This table summarizes Shannon's estimates of English entropy based on his experiments. He used different amounts of context, from a few letters to over 100. As context increases, the entropy per character decreases, because more context makes the next letter more predictable. The final estimate of 1 bit per character is a landmark result. It tells us that English is highly redundant, and that a good compression algorithm can achieve a compression ratio of about 4 to 1 compared to ASCII encoding. This is because ASCII uses 7 bits per character, while the entropy is only 1 bit. The table illustrates the trade-off between context and predictability. More context reduces uncertainty, but there is a limit to how much reduction is possible. Shannon's noiseless coding theorem is the cornerstone of information theory. It states that for any source with entropy h, the average length of any uniquely decodable code must be at least h bits per symbol. Moreover, there exists a code that can achieve an average length arbitrarily close to h. This theorem gives a precise meaning to entropy. It is the fundamental limit of compression. No matter how clever you are, you cannot compress below this limit without losing information. This is the answer to our original question. The ultimate limit of compression is the entropy of the source. The theorem also implies that any lossless compression scheme must have an average code length at least equal to the entropy, which is why entropy is a key concept in data compression. Let's review the key numbers we've encountered. The naive code uses 2 bits per command, while the smart code uses 1.75 bits. The entropy of the command distribution is 1.75 bits, which is the theoretical minimum. For English, Shannon estimated the entropy to be about 1 bit per character. These numbers illustrate the power of information theory. It gives us precise limits on what is possible. In finance, we can think of these as the cost of information, the minimum resources needed to transmit a message without loss. This perspective is useful for understanding the efficiency of data transmission and storage, and it has implications for designing communication systems and data compression algorithms. We started with a simple question: how small can data be compressed? We ended with a profound connection. Compression and prediction are two sides of the same coin. Shannon's information theory gives us the mathematical foundation, and modern AI is built on it. When a language model is trained to predict the next token, it is effectively learning to compress text. The better it compresses, the better it understands the underlying structure. This is why some researchers say compression is intelligence. If you want to understand AI, start by understanding entropy. The journey from a simple coding problem to the foundations of AI demonstrates the unifying power of information theory. Markets reward discipline, not certainty. If this analysis helped, like the video and subscribe to DeepQuant. Tell us in the comments which market idea we should test next. Evidence beats noise. Control risk before chasing returns.